Good morning, and thank you for attending this talk. My name is Marina Zapater, and I am an associate professor in the School of Engineering and Management of VO in the University of Applied Sciences of Western Switzerland. So today I'll be giving you a talk on the tools we have been developing in HES-SO and in collaboration with EPFL, and particularly on gem5-X and gXR5, and how we are performing full system simulation in order to explore and enhance heterogeneous architectures. So all this work that we have been doing is a research in collaboration between EPFL and the University of Applied Sciences of Western Switzerland, and you will be seeing also chunks and pieces of all the research we have done in the talks that come also after my talk. So first, why doing architectural exploration? So just let's start by a little bit of motivation. So as you know, multi-cores are growing fast and are becoming more performant. So at the beginning, it was enough to just increase the number of transistors on the chip. At some point, we saw that the single-thread performance started to stagnate, and we decided to go for multi-core. And what we are seeing now is more and more powerful chips with more and more cores, and even becoming heterogeneous. That is, where we put GPUs, FPGAs, etc. in order to attain even a higher performance. So the thing is that, as you know, computing is more indispensable than ever. Data centers and cloud computing are serving a myriad of new applications. So before, it used to be when we spoke about high performance computing, we were just thinking about gene sequencing, financial simulations, molecular dynamics, weather prediction, typical HPC. But today it's way more than that. We have medical analytics, we have video streaming for like platforms like Netflix, etc. We have artificial intelligence and online gaming. So what all these applications have in common is that in the end, they are tackling very huge data sets, and they have some stringent quality of service requirements. They have some real-time requirements. And more specifically, within all these myriad of applications, we know that artificial intelligence, AI workloads, are in all the aspects of our daily lives. And furthermore, they have started to span beyond the data center. So some of these workloads are no longer only data center constrained, but they are also going to the edge. And then here comes the issue. So we need to be tackling efficiently workloads that will be moving from the data center to the edge, and we have to tackle them seamlessly. Because, as you know, today the importance is on creating value out of the data. So basically, our edge devices will be collecting data, will be processing data, and all the data that they cannot process, they will send it to the data center. Which brings up with a new challenge, which is we need to have efficient multiprocessor system on chips, and these efficient MPSOCs need to be on the data center, need to be on the edge, and we need to tackle power, performance, and thermal challenges. So how do we do this? How do we do this efficient, high-performance, multiprocessor system on chips? Well, there are two things that we can do. The first one is managing them efficiently. That is, doing some kind of multi-layer hardware-software management, like tuning the frequencies of the cores, like improving the task allocation, etc. But the other one is working on novel architectures. That is, creating radically different new MPSOCs with very out-of-the-box and new architectural enhancements. So in this talk, I'll be focusing on this second part, on the part of the architectural enhancements, and we'll be telling you a bit more how we propose to explore these new architectures. So if you think about how to enhance architectures, many ideas come to mind in order to overcome these two walls that we have today. So today we have the power wall mainly and the memory wall. And today, not only in my talk, but in the talks that will come afterwards in the morning, we will see a few options to overcome these walls. Specifically, Irem and Alex will be speaking about in-memory computing techniques, or that is, trying to bring the computation closer to the memory or the memory closer to the computation in order to be more efficient and to consume less power. And the other technique we'll be seeing today, which Sergi will be telling us, is how we can use faster interconnects, and in particular wireless interconnects, between the processor and the memory in order to speed up computation. So in the end, regardless of the techniques we applied, the challenge remains the same. And this is why we're doing this tutorial. The challenge remains on traversing the hardware-software stack while obtaining accurate results. Okay? So just keep in mind that new architectural enhancements in the end will be coming from the hardware, device, or technology level. For instance, we might be working on new types of bit cells, new types of memory devices, and what we want to do is to incorporate that into the architectural level. But in the end, what you also want to do is to be able to assess those results, the accuracy of those results, not only at the circuit and not only at the architecture, but at the overall application. So when you run an application from a user, how does my whole stack behave? So in the end, this is the big question that we are trying to solve. It's how do we bring them up the stack so that we can test with real applications? How do we traverse from the technology to the circuit, to the architecture, to the system level? How do we provide support at the software? How do we provide support to run an application, a user application? It can be a TensorFlow, it can be a CNN written in TensorFlow that somebody will be running with all the libraries of the system on top of a Linux operating system. Well, so the answer to our question is we propose to use architectural simulation, and specifically Gem5. And as you will see, the enhancements we've been working on top of Gem5, such as gem5-X and gXR5. So let's speak a bit about Gem5-X. Okay, so what is Gem5-X? So first of all, it's a Gem5-based simulator in which we have added some architectural extensions. So the name stands for Gem5-based full system simulator with architectural extensions. And what we did with Gem5-X is providing or trying to provide out-of-the-box simulation of a wide range of architectural extensions, including the capabilities of extending the Gem5 ISA of an ARM system, putting in cache computing, scratchpads, HBM2s, etc. But it's also a methodology for the optimization of many core heterogeneous platforms. And today I'll be also talking a bit about how we are applying this methodology. So the way we see it, what we need to do is to run user-level applications, whatever application it is, characterize it, and optimize the architecture. And then iterate the loop until we meet certain constraints, the constraints we're looking for. And then we can say that we have achieved an optimized architecture. And also, this is also important, Gem5-X in the end, it's the result of our journey trying to learn Gem5. So basically, when we first downloaded Gem5, we did what everybody does, try to download, try to run, see what happens. And then we faced many issues, many things that were not working the way we wanted them to work, many images that were outdated. And then Gem5-X is also an effort of trying to put together a lot of enhancements to make our lives easier when running Gem5 simulations. So more specifically, it's support enhancements and validation. So first we were looking for scalability. So what we did is we are trying to open source something that is out-of-the-box simulation, a complete environment, a full system simulation that works. We are basing ourselves on the Gem5 core of August 2018, and we provide working simulations for Intel, ARM32, and ARM64. And then it means that we can run an Ubuntu, that is an Ubuntu system with a decently recent kernel, and where we can even run inside the Linux OS, we can run some containers in case you want to give it a try to virtualized applications. Furthermore, we also incorporated inside the simulator the capability to use gperf, because what we want to do in the end is to characterize how the applications work inside the Gem5 simulator. And we are providing enhanced checkpointing to speed up the simulation, to stick always to the region of interest, and also hot swapping of disk images in order to enable researchers, PhD students, whoever, to just be able and work faster with gem5-X. A very important point also that we wanted to do is to validate that everything matches the performance of your systems. Because the issue with simulators, is that you can simulate everything, but what we want to make sure in our research is that the numbers we get are the closest possible to the reality. So how did we do this validation? So basically what we did is to try and match the performance against an ARM Juno board. The ARM Juno board has in-order and out-of-order cores, so we were trying to just play around and match exactly the number of edge units, the number of functional units, execution stages, the latency of functional units, everything, so that in the end we could compare what is the performance of a certain benchmark in Gem5 and in the Juno board. And what we found is basically that we are able to obtain errors which are below 4% when compared to the execution on Juno. So we mean comparing the execution time of a benchmark in the Juno board, the execution time of a benchmark in Gem5-X, and that difference is below 4% for both in-order and out-of-order cores. So what else did we do? So at that point, we already had all these support enhancements to make our lives easier when simulating. And then the next step for us was to do the architectural enhancements. That is, at least providing to ourselves a backbone for a wide range of extensions. So what are these extensions that we were working on? So the first ones that we will be seeing briefly in this talk, but also afterwards in the talk of Alex, is in-cache computing and hybrid caches. We'll also have 3D stacked memories, and in particular HBM2s, and then on scratch parts and extensions to the ARMv8 ISA. How to extend the ARMv8 ISA in detail, it's something that you will see this afternoon during the hands-on tutorial sessions. So let me start by an example case study of how we can find the best architecture for a certain application. And this certain application that we were using is video analytics. So what is video analytics? So this case study is, you can imagine it as running a pipeline in which we do first video streaming. So we do some kind of encoding process, and then analytics on the images that we have encoded. You can think of it as video surveillance cameras, the typical application of video surveillance for smart retail, for smart cities or smart cars, or for traffic control. So you're basically encoding video and processing, doing some analytics, some convolutional neural networks. And the goal here is to show how, by using Gem5-X, we can see how we can use some architectural enhancements, such as in-cache computing or HBM2 memories. So let's start first by the use of in-cache computing. And we start first by seeing how we can speed up the first part of the pipeline, which is the video encoding. So to do this, what we did is we were characterizing and exploring how different cores behave using Gem5-X. So the first thing we tried is, let's give it a try at different types of cores, in-order versus out-of-order cores, to find execution bottlenecks. And the first bottleneck that we found is that the fear filtering that happens during the encoding exhibits a very good level 1 cache locality, which means it's a very good candidate for in-cache acceleration. In the end, what we are trying to do is simply to analyze which are the chunks that take most of the time and how we can accelerate those chunks. So what does in-cache computing acceleration mean? So Alex will be telling us a lot of details on how this works from the circuit and the technology level. But just to give you a very brief explanation from an architectural system level, what we are doing with this in-cache computing is that we add a little bit of extra logic to the cache, to the L1 cache of our system, in order to be able to perform simple computations. That is addition, shifts, etc. And basically, because the FIR filtering is basically additions, subtractions, and shifts, it's a very good candidate to be accelerated by this in-cache computing. It will allow us to reduce the energy. So what we are looking for is to reduce the energy and to enhance the performance of our system. And we were trying that for different types of cores, at different types of frequencies, and for different types of input videos: high resolution, low resolution, medium resolution. And what were our findings? So basically what we could see is that for both types of videos, low and high resolution, we were able to enhance the performance and reduce the energy of the execution when picking up the right type of architecture. By right type of architecture, it was, for instance, in-order cores with in-cache computing for the execution of the encoding, and we were getting a 15% overall speed up for the application. So this was for the encoding only. What we did afterwards is, okay, what if I go and look into the whole pipeline? The whole pipeline being video encoding plus video analytics. And then we said, okay, we know that this will be also bottlenecked by the connection to the main memory. So what we decided is, okay, so let's go and see how we can build a heterogeneous architecture in which we have regular in-order cores, ARM64 in-order cores, in order to run the part of the CNN. And then we will be using in-order cores with in-cache computing for running the part of the encoding. And then we are connecting this to a high bandwidth memory using the global interconnects. And we will be using an 8-channel memory, 1024-bit bus, and 3D stack DRAM4 memory banks. And we allocate separately the two different applications. So this is a kind of a very heterogeneous system, but it has CPUs with and without in-cache computing, and also a very nice memory hierarchy, very fast memory hierarchy. So what we found is that we can speed up the application by an extra roughly 8% for each of the stages of the pipeline. And the interesting conclusion is that both applications benefit significantly from the architecture, because we are basically tuning the architecture towards the specific applications that we want to run. So finally, what we were trying to do in the end with this research is, what we can do is to combine gem5-X with with tools for power and thermal modeling and characterization. So in the end, what we want to have is a full suite of tools to find the best performance, power, and thermal trade-offs for our applications. Then it means that we can use gem5-X for performance characterization and to explore the different architectures. We can combine that with power modeling, either using MacPath or either creating our own models, our own power models, and then just putting that together with thermal simulation using 3D-Eyes, which is also a tool developed at the EPFL. So until here, I told you quite a lot about how can we do this architectural exploration, why do we do it, etc. But probably at this point you are still wondering, like, okay, but how do you traverse the hardware-software layers? So how do you go from the technology up to the system level? So of course, all the tiny details, you'll see them this afternoon on how exactly what we change and how we change it in Gem5. But let me give you a detailed example of how we can do this using hybrid caches. So this is an example that we have of hybrid caches for CNN acceleration in edge devices, okay, not in servers, in edge devices. And the goal of this research was that Basically, edge devices are very much constrained in terms of resources, and even small networks for edge devices can have a footprint of in the size of megabytes. And within that footprint, we know that the weights of a CNN can account for almost 40% of all memory accesses in the inference and have a very high read-write ratio. That is, weights are basically something that is read over and over and over again, whereas inputs is something that tends to be written and read more often, okay? So having this in mind, a research idea came to our heads, which was, okay, let's take advantage of this to try and do something more efficiently on our cache. So now what we are proposing is, instead of having a regular cache, the regular cache has a technology which is the static RAM, SRAM. We're going to use non-volatile memories. So non-volatile memories, like resistive RAMs, they have a large density, but they have a smaller leakage than the SRAM, that is, smaller energy consumption. But their issue is that they have limited endurance. That is, you cannot write to them very often, or you will degrade their reliability. So what we decided is, okay, so let's just propose a system in which we have a hybrid cache, a mixture of SRAM and NVMs. Okay? Good. So this is something, the numbers themselves from the technology level, it's something that we could obtain. But the thing is, how do you put this on the system and how do you simulate this at the system level? So what we decided is, okay, let's design a hybrid cache from the computer architecture perspective. We'll put regular ARM cores, we will put a regular SRAM hierarchy, but we will duplicate the hierarchy just to have a resistive RAM next to our regular SRAM, like this, like what you can see in the image. And then what we will do is, everything that is weights to the neural network, this will go into the resistive RAM. Whereas everything that is inputs, it will go to the regular static RAM. And in this way, we will be able to take advantage of the benefits of one and the other. So basically, as I said, for efficiency enhancement, we use resistive RAM for reads, we use the SRAM for writes. And then what we would like to do is something like this exploration. We want to explore for different types of networks, Inception, ResNet, SqueezeNet, for instance, what is the power reduction and the performance gain for different sizes of the cache. So what is the solution to perform this exploration? gem5-X. So in order to bridge the gap from the circuit to the system level and to traverse all the layers in between to end up in the software, what we do is we start from the hardware level implemented in gem5-X. That is, we incorporate circuit level models. These circuit level models can be obtained in many different ways. You will see on the talks of Alex or Irem or Sergi how you can obtain those models. And once we have the per block performance and even power data, what we do is that we will plug that into Gem5. And we will be implementing that into the architecture. So that is, we will create new models, we will create new architectural enhancements, we will change the underlying models of Gem5, and you will see how to do that on the tutorial of this afternoon, until we get, for instance, an architecture of a hybrid cache like the one you see here. That is, we will duplicate the level 1 hierarchy in order to include this hybrid cache with resistive RAM and with a static RAM. Once we do that, of course, we need some OS level support. The way we do it is that we will reserve a region of memory in boot time that we will devote in order to place what we want to place. In this case, the reserved memory chunk will be for the weights of our CNN. And then afterwards, the only thing we need to do is to create a C++ user library for this new hybrid cache that we called Shy cache, and new functions that will enable me to malloc and allocate the regions that I had reserved during boot time. And once I've done that, I will have my new user library and I will be able to use it. So I will have an application that will be able to use that user library in a seamless way from the application perspective. This means that you can potentially run any application that you want because you will have all the underlying software support that you need. So you will basically have this full hardware-software stack simulations. And you know that this will be accurate as long as the circuit level models that you have developed are accurate, and everything else should be preserving the accuracy. So far in this presentation, we have seen how you can use gem5-X for architectural enhancement to just test and propose new architectures. Of course, as I said, on the tutorial of this afternoon, you will get all the details, all the fine-grained details of how this can be done. So stay tuned for the tutorial of this afternoon. Just to tell you, gem5-X has been open sourced since April 2019. You can download it. You can subscribe to our mailing list. You have the code available in GitHub. You have patches. So in the end, what gem5-X does is it patches the Gem5 installation and works in a very similar way to Gem5. And just remember to check out the VM that we have prepared for you for this afternoon's tutorial. Give it a go, and hopefully we will be able to solve all your questions on how gem5-X works and why is it useful. So just keep in mind that very last thing, our latest new adventure is gXR5. Okay, the goal of gXR5 was to provide full system support for RISC-V, for RISC-V architectures, and you will also see all the tiny details of what is working exactly. Just to tell you very briefly, and afterwards Josh will tell you more details. gXR5, what it does is it's the first Linux-capable full system simulator built into Gem5. Before gXR5, the support of RISC-V architectures was only on system emulation mode and was quite limited. And as I said, you'll see a premiere of all the features and capabilities this afternoon. So gXR5 will be available, same than gem5-X. It will be available on GitHub, open source, really very soon. But if you want early access to the code in order to start testing everything, just send us an email, to Josh, put me on CC, and we'll give you access to the code given that you have registered to this tutorial. So thank you for your attention, and if you have questions, I'll be very happy to answer. And here you have my contact information. Thanks.